That's great. So first of all, I am Anton Spaans. I am working for Accenture. I've been working at Intrepid for the last 4 years, and Intrepid was acquired a couple of years ago by Accenture. I've been doing Android development since 2008 on a tinkering / hobby scale, and I've been doing it professionally since 2011, give or take. And so yeah, I've been through the whole life cycles of all the versions of Android for quite a while now, and I'm still doing it. And of course, like a few years ago, Kotlin became popular, which is sponsored by Jetbrains. Google made it also first-class citizen and became wildly popular as one of the fastest growing languages out there. And we are full in as well. And I'm one of the organizers together with Russell, who is currently not online, of the Kotlin office hours, which is also held once a month, normally at our offices, but in these times it's held online every second Thursday of the month. But lately that's also a little bit flexible because of all that's going on. Okay, let's start. This talk is about Kotlin types. What are they? Why do we use them? And what is so specific about Kotlin with respect to other type languages? So why do we have types? What are they used for? Well, if you write code, you want to be sure that your code works. So if you write a function and you need to figure out whether the given inputs result in the desired outputs, you write tests around it. But if you have types, the type system of your language can already prove a lot of that stuff. So you don't have to write your tests around it. So some inputs can only allow certain values, certain types, and the other inputs cannot. And your output then is also limited to a particular set of types that can do only a certain set of things. So that's the type system of your language can kind of prove that, and you don't have to write tests for that. So if your function takes a string, you don't have to test whether the result is fine if you give it a number. That's kind of the whole idea behind it. What is a type? A type is basically a set of values. And with the set of values, we have a set of rules associated with them. Here is an example, two types. We have a Boolean type that has only two values, so true and false. And an integer has an infinite amount of values, but it's basically all numbers from minus max int to plus max integer. And on a Boolean, you have a bunch of operators like OR and 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 XOR and NOT and that kind of stuff. And on an integer, you have a different set of operators like plus and minus and times and absolute value, all those other things. So the amount of values that are in there and the operations you can do of these values define the type. A type system can check for that. So for here example, we see that we have a Boolean called is visible. We give the value true, is one of the valid values, and a number, we give the value 4. And we cannot assign willy-nilly. We cannot assign a number to a Boolean. Your compiler, the type system of your, if you have a statically typed language, will produce an error. The other way around, just the same thing. You cannot assign a Boolean to a number. The limited set of rules, you cannot call times on a Boolean, and you cannot call and or a number and expect a Boolean value back. For subtypes are basically a subset of another type. So here, say that the gray circle is all the shapes that are available. And inside we have all the circles that are available. So we have a rule on shapes. We can calculate the area, the square yards or whatever it is. And on circles, we can ask for the radius. So here, when we try to assign a circle to a shape, it's fine because a circle is always a shape. That's a given. So now you can have some kind of polymorphic stuff going on. Basically, you can treat a shape and assign it another, and assign it a circle. In this case, you see here a wheel being assigned to a shape. But the other way around is not possible. So you cannot assign a shape to a circle. That's not possible. Why not? Because the shape might not be a circle. It might be a square or a triangle or some other shape. So in this case, you kind of see what subtypes really are. Subtypes kind of define the assignability of variables. So in this case, it means that you can assign a subtype to its base type. In this case, you can assign a circle to a shape, but not the other way around. That gives you some flexibility and still have safe code. And what does safe code mean? That if I have a shape and I call, for example, a radius on it, it's always good. But if I had a shape and I could assign it a square to it, then radius wouldn't make much sense. And radius would go wrong because radius is not defined on the square. So these are basically what types are in very in like an overview. Are there any questions about types in general and subtypes and assignability? No? Okay, then we move on to types, how they are defined in Kotlin. In Kotlin, we have a specific type that's not unique to Kotlin, but it's one of the few languages, and it has nullable types. Nullable types means it can have the values, any of the values of the given type, or null. So in the top example, we have a variable called name. It's a string, and to assign it a null there, that won't work because it's not nullable. I cannot assign it null. The one below it is its type is called string, and then with the question mark behind it. So that means that the values are all the string values or null. That means that the assignment below that is fine. So what does that really mean? If I assign it a value here like ABC, which is fine, and I name the length on it, I will always get the value 3 back if the value is ABC. On a nullable, it can have a condition that either returns ABC or a null value. Then how do I get stuff out of that name? How do I can do things on the nullable type? Well, the null value has basically two operators. It's the question mark dot followed by a property or a method or a function. And if the value itself is null, the function or the method called upon it will also immediately return null. It will not do anything with it. The other operator is double bang, the double exclamation mark. So in this case, it will return, if it's not null, the name itself, or it will throw a null pointer exception.
I have a question. I don't know, I've been using Kotlin for about 1.5 years, maybe 2 years now. And I've never found a good use case for a double bang. Every time I've considered it, somebody's put it forward in a PR or I've considered using it, turned out that it always was an unsafe option. I mean, if you want to throw an exception, you're better off explicitly saying that you want to throw an exception rather than have it happen. Have you ever hit a case where a double bang was an appropriate operator to use?
There are a few times where it's kind of appropriate, but yeah, in general, when you see double bang, it's a code smell. You should really take a hard look at your model and at your data and at your method to see if you can get rid of it in a good way. Often when it's an input parameter to a function, you really want to have something like require not null or some kind of precondition check on it. And then a message that's being thrown with your exception if it's indeed null in this case. But during the execution of the body of a function, some things might be returning null values. And on occasion, calling double bang on it might make sense. but it really depends on your use case. I could even argue the same for a question mark dot, because you kind of ignore whatever follows after. So in this example, like name question mark dot length, so I get null back instead of really the length, which kind of, okay, I do not throw an exception right now, but I just keep getting null back. So am I kind of burying my error? Should it really be null there? So I would argue, yeah, if you see double bang, that's a pretty strong code smell. So try to get rid of it. But sometimes you really want it. If you see question mark dot, it is a little bit of a code smell. You might want to think about it, but you see that used more often.
Thank you.
So here we see nullable types, and now we're going to take a look at a small overview of the Kotlin types hierarchy. So on top of the hierarchy is any, which kind of functions as the object in Java. Subclasses of any are unit and int and string and pair and tuple and, well, you name it, like a whole list of objects, object types and classes are subclasses of any. And of course, they have subclasses and they have subclasses and they have subtypes. And on the bottom is the class nothing. We will talk about nothing a little bit more later, which is a subclass of all other classes, which is kind of interesting. And we have nullable types in Kotlin, so they kind of sit right next to it. So an any, nullable any is a subtype of any. And a nullable int is a subtype of int and a subtype of nullable any. And that is basically kind of mirrored that way, kind of shifted and then mirrored in the same way. Here we see a few of the special Kotlin types, any, unit, and nothing. The any class is basically the base class of all other classes. It's like the object class in Java, for example. It's an open class, so this is how it's defined. Open class any with a few methods on it, like hash code and some other little things. Another type is called unit. The unit has only one value, and the value is also called unit. It means nothing because it's a type with only one value. So if you get the value back, it literally means nothing. You cannot do anything with it. So it kind of represents the void return type, the capital V in Java. And the third special type, which is the most funky type because you really have not anything like that in Java, is called nothing. You cannot create any value of nothing. Nothing has no values. It's an empty type. It's like an empty set. It's literally empty. Hence the name nothing. Let's take a closer look at unit. As I mentioned earlier, it only has one value, unit. It's the value unit, and it's the default return type of a function. So if your function return unit, you don't have to write it down. And it's the default return value of the return statement. So you can do return, or you can do return unit, which is exactly the same thing. Here you see a bunch of combinations of using unit and not using unit. And all four statements are exactly the same. They're not different. The type nothing is the funny one. Is basically is the type that has no values. It's a subtype of any other type. And how does that work? How is that possible? Well, if you think about it, a type defines a set of values. You can carve out a subset of values, and that will be the subtype of that type. The empty set is basically a subtype of every other type. Every set has an empty set in it. I mean, it's kind of weird when you think about it, but that's kind of the case. So that's the reason why nothing is a subtype, a subclass of all the other types. And it comes in really handy. So if you look here at the code, I have an answer. If something is done, I get 224, and otherwise I call a function called fail that returns nothing. So how come that answer can be an int in this case? How does this work? Well, either an int is returned in the form of 224, or a nothing is returned if the fail was called. So basically, the answer must be the common base type of both of them. Well, the nothing is a subtype of an integer, so the common base class of the base type of that is an integer. So answer can be an integer in this case. Are there any questions about the nothing?
Yes, Anton, this is Lou. I have a question. So in this case here, how come int is not an optional? I mean, nullable.
I could make it nullable, but it's not. Because nothing is a subtype of an integer. So then it's fine. So this code compiles. I either get an integer or I get a subclass of an integer in the form of a nothing. So answer can be an integer. So how does that work?
So I'm imagining like if you were to run this code and we get into the else case and let's say that we're not throwing an error in there, but we're printing something or doing something else. Yeah. But then that means that the value of answer is nothing.
No, it's
right?
No. Fail. So if it's not done, if done is false, we go to the fail, and then it will stop because I throw an exception.
No, but I'm saying if you did not throw an exception, what would be the value?
I cannot not throw an exception. I have to do something here. So fail can never return. So that's actually the next slide.
Okay, that makes sense.
Yeah. So basically, if fail is executed, nothing can follow. If nothing is returned, nothing can follow. And that's basically what I'm showing here. There's also kind of a funky thing that's very particular to Kotlin. The return statement itself is an expression. And the return statement returns nothing. So in this case, this is valid code. So it returns 5, and it returns actually the value 5. But I can make it an expression by assigning it to something. The code underlined and in green will never be executed. And actually, IntelliJ will give you a warning about that, because I just returned 5, and anything, the zilch assignment won't happen. But it's valid code. The same happens with the throws an exception. So the assignment to zilch there also will never happen because I just threw an exception. And if a function does return nothing in the third line, that means that anything following it will never get executed. So it's not an error to have the val count equals get count there, but you will get a warning in IntelliJ that tells you that sorry, but you might as well remove this code because this will never get executed. So with this, you can actually have very, very funky Kotlin code. You can do return 10. It's perfectly valid code.
I figure that's how you code usually. How many returns do you prefer, 5 or 10?
3 is a nice number.
If you have a function that returns 5, is the return type of that is still integer, right?
No, if you do return 5, you get then you return nothing again. So
so the return type is nothing.
Yeah, because then the returns 5 its return type will not be int, it will be nothing.
Right. Interesting.
Yeah, it's so don't do that. But the thing is, because returns a nothing can follow. No other code can follow. So if you have a return statement and you put code after it, because return itself returns nothing, the IDE will give you a warning like, oh, you should not write any code after that. You should not write any code after the throw statement either. So basically, that's what it's also for.
There was a comment in the group chat from Matt T. It says, I believe this is how the to-do works in IntelliJ as a placeholder that still compiles.
Yeah, to-do is basically, that looks exactly like throws an exception. That's what it does. To-do is a function that throws an exception. Always an exception. So that means if a function returns nothing, it says this function will never return, or it will never exit normally. You know, it can exit through an exception, but will never exit normally. But yeah, exactly. That's how the to-do works in Kotlin. So we also know that nothing, like any other type, can have a nullable, can be nullable. So what is a nothing question mark? Well, it's the empty set, so nothing, or null. So that means it's null. So nothing question mark has one value, null, and that's also the type of null. So the value null, if you do val number int question mark is null, you can do that. Val name string question mark equals null. The other one is not possible because nothing, nullable nothing is not a subtype of string. It's subtype of a nullable string. But if you would leave out the type specifier, for example, val my value equals null, that my value will then have the type of a nothing question mark. That's how it's inferred. So null has its own type. It's called nothing question mark. A bunch of us come from Java, and a few Kotlin types have their associated Java types. Capital int is like a lowercase, like a primitive int in Java. An int question mark is the integer object in Java. So we have an array of int, which is an integer array, a list of int, a list of integer, and an int array is the primitive again. And we saw the other ones like any is an object, a unit is like a void, and nothing does not have any equivalence in Java. Like Java, Kotlin can have classes. Classes can be instantiated. You can create a value out of a class. So basically a value out of the set that is defined by that type. Class can carry state. So I can have a shape that carries a name value. Here it has the string shape. And they can be extended. It's nothing new. If you are familiar with Java, this looks very familiar. You have abstract classes. Abstract classes are kind of like classes, but they cannot be instantiated. They still can carry state and data. Like here, it carries the data for the property name, and they can be extended. And very much like Java again, interfaces. Like abstract classes, interfaces cannot be extended, but unlike classes or abstract classes, interfaces cannot carry any data or state. So the is equals or assign the string square to the name, that's impossible. But they can be implemented. They can be extended or implemented, depending on nomenclature that you want to use. Another thing that is, it's in Java, in the more modern versions of Java, but Kotlin also allows for default implementations of your methods. So you can assign a particular default implementation of a method that is defined in your interface. You can even do that with properties, as long as you don't assign data to it. You have to just write the proper getter and setter for it. Kotlin also knows about singletons. There are two ways of defining true singletons in Kotlin. What do I mean by a true singleton? A singleton is basically a value of a type, and that type has only one value, that particular singleton, and that value is valid through the entire lifetime of the application. It is always there until the process dies. There are two ways of defining that. You can declare a companion object on a class, interface, or abstract class. And here, for example, I have my interface shape, and I define a companion object on it, and I have a method called createShape. So this is kind of like a factory almost in this case, in this particular example. So I can assign shape.companion. I can assign shape to my factory, and then I call createShape on it. Shape is basically shortcut shape.companion. So these companion objects are often used to mimic the static classes or the static methods in Java. Another way of defining singletons is through an object definition. An object definition, its name is its type. So in this case, I have the value shape factory. Its type is shape factory. And in this particular instance, I created one method on it, createShape. Are there any questions about singletons? Okay, then I'll move on to the last particular type that are.
Actually, I guess I have a question about singletons. I guess I've never really thought about this aspect before. But
Unique or different from Java than static access. So that you don't have static methods in Kotlin. They always have to be tied to a particular object. So you can have your object, your shape factory. You can extend it from an interface if you want to. So you can have it implement certain things. So it's a really strong, and also your companion object can implement classes or extend interfaces, extend classes or implement interfaces. So it's a really strong feature of the language.
So the question I have is, if you define a property in a companion object or an object, just val equals some value, are you saying that value will persist as long as the application exists, and therefore you should be conscious of trying to avoid that, and that would be just unnecessary performance hit most likely?
It depends, but yeah, that will be global state. Absolutely.
Interesting.
Yeah. Another type is function types.
Yeah. The difference between an object and a companion object is interface, or sealed classes have companions too, don't they?
Yes, any type of class, any type of extract class, any type of interface, any type basically can have a companion object.
So why do you have the object on its own as well as the companion object? Does it ever go on its own?
Well, this is basically a companion object that's tied to a particular type, in this case, an interface shape. And you can access it by the type name. So it's kind of a syntactic sugar. Here you're allowed to basically have a top level object, be its own type and value. So not within, so its own namespace. Yeah, it's not shape dot something. It's just shape factory. That's it.
Okay.
But yeah, often it's a matter of taste how you want to write it. So this could be, these two are.
Yeah, thank you.
Kind of interchangeable. It's a matter of taste. I would go for this one because they're kind of related. This companion object is a factory of its shapes. I would use this one in this particular example. But this is valid too. And other types are so-called function or function types. You can assign lambdas and functions to these to variables of these types. Here you see A and B. A is the type that is the input to the function, and A can be actually a list of types. It could be A, B, C, D, etc., etc. So if the function has more than one input parameter, and the return type appears after the arrow. You have extension functions. I'm not going to explain exactly what extension functions is. I would say Google it and look at it. They're really, really powerful mechanisms in Kotlin to have context-aware computations. But basically, here, this is an extension lambda. So the this values of type R, and it takes an input of type A and returns a B. And you have the suspend variations of them as well. So here you can see that the rotate operator takes a shape as the receiver, and then the number of degrees is a double, and it returns a rotated shape. That's what's showed in the example below. They are full types. These things that look like, you know, with the arrows, and you can extend them, you can implement them, and you can all things you can do with regular types. Before I move on to generics, are there any questions?
Can you like subclass a lambda? Like, is there a subtype for a lambda?
Yeah. You can do that. You can do class my type colon A arrow B. Yeah, you can do that.
Mm.
They're full types. Yeah. They're actually interfaces in that case, because these things are the interfaces. But yeah, they're really cool. Okay, let's move on to generics. Generics are often used if the type operates on another type. And then if there's a common pattern in all these operations that happens on that other type, you can bundle them in an interface or in a class. Very common examples are like lists and functions and such. Here you see that a list takes an input of type T, and then it has an operator that gives the the element at the given index, and it will return an element of that type T. The function, I get a type I in, whatever it is, that I decide what it is later, and I get an output O back. And you can carry it forward. An array list of T is a subclass of an abstract list of the same type T. Some instantiations of these types. So list T, I instantiated as a list string. Now I have a particular list of strings, and I can get, you know, a string back if I call the get function with the value 5 or any other int. A retrieve name, I can do retrieve name invoke of 5 because it's an int as input, 5, and I get a string back. The O is a string, so I get a name that is a string back. And I can put any type of my desire. Instead of int, I could have done double. Instead of string, I could have done some other custom class or whatever I want. Any questions about generic type parameters? It's very similar to what Java offers. Let's move to the next one. So in the previous slides, we saw that the type T, or for example, of a list, could be handled by a list interface, for example. But you can also put an upper bound to it. So here I have a fruit box, and I can do stuff on fruit in that fruit box, but every type needs to be a fruit or a subclass of fruit. That's what's being expressed in the fruit box classes declaration. So if I try to create a fruit box with an animal, like a lion, I get an error. Or if I try to create a fruit box with an any, I also get an error, because any is not a fruit and lion is not a fruit. If I don't do colon and then the upper bound, it will also always default to the upper bound of any question mark, which is the topmost type available in Kotlin. Are there any questions about upper bounds? It's very much like the extends clause in Java. Sometimes the upper bounds can be a combination of interfaces. So in this case, it's not just fruit, but it also has another upper bound. And then you can use the where clause. So here I have a sortable car sequences class, and it can have a type T. And type must be comparable because I need to sort them, and they must be of the type har sequence. And this is how you specify that by the where clause, and then a comma separated list of upper bounds.
I haven't seen where used ever before, and I am going to have to research. I have no questions because I'm just so lost with it.
In Java, you use the ampersand to do the same.
Another feature I never used.
And here we come in the last part of my talk is about generic variance. What is variance? So let's pose a question. Say we have a class, a human, which is a subclass of animals. So all humans are animals, sorry. And so if I have a list of humans, can I assume that a list of animals is its base class? So basically a list of humans is a list of animals. Is this possible? Is this safe to do this always? So basically the assignment of list of humans to list of animals. Well, the answer is that it depends. It depends on what you're going to do and how with the list of animals and how the list is defined. So let's take a quick peek in it. So first, a little bit of an example. So we have the animal. It has a method called getAge, and we get the age of the animal out. I have a human, and the human can talk, and words come out. And an amoeba can split, and we get 2 amoebas. So with that in mind, let's go to an example. And the example is called covariance. I'm going to explain covariance as I go along. So here I have the interface list again. And T must be at least an animal. With the get, and in the index, I get an animal out. Then I have to see a question. If I have a list of humans, can I assign that list of humans to a list of animals? Well, as only get is defined on that interface. So if I do animals.get1, I get another human back. And yeah, another human is also an animal. And so it's fine. So I can assign a human to an animal, and there's no problem. Can I do it the other way around? So I have a list of animals right here. There's a human and an amoeba in the same list. And then I try to assign the list of animals to a list of humans. Kotlin will say, no, this is not possible. It will show you an error that it says a list of animals is not a list of humans. Why not? Well, let's try it. Say the red line, the error line, actually did compile. So that means that humans.get1 returns me a human because it says it's a list of humans, but it's not. The first, the item on index 1 is an amoeba. So here we have a problem. So this assignment is not valid. I'm trying to assign an amoeba to a human. So to prevent the last mistake, the assignment of the value X, the assignment actually of the list of animals to a list of humans is prohibited. That means that in this case, if a human is a subclass of animals, a list of human is a subclass of a list of animals. So the assignability, the subtype arrows point in the same direction. And that happens only when the interface defined only produces values of that given type. In this case, that is true because get produces a value of value t. It never consumes it, it only produces it. And in this case, this holds true. So now we have covariance, and it's called co because they point in the same direction. Any questions about covariance? Let's say now we go to contravariance. You probably can see where I'm going with this. It's like here I have a box, and instead of, I can put an animal in a box. So I have a human box. I can, if I put a human in a box, it starts talking, complaining, doesn't like it. And if I put an amoeba in a box, it starts, stressing out and splits itself. So let's see what happens if I try to do kind of the same thing that we did with the covariance. So here I have a human box, and I try to assign a human box to an animal box. Is this possible? No, it's not. Because say I have an amoeba, and an amoeba is an animal, and I'm trying to put it in the animal box. The compilation would in itself hold, but actually because animal box points to a human box, I try to put an amoeba in a human box. So the first parameter of a human box was a human, not an amoeba. So you will get a class cast exception on the put assignment if Kotlin didn't prevent me from assigning the human box to an animal box. So that's not possible. So the assignment goes the other way around. Instead of producing, I'm now consuming a value. I'm assigning it to the function in one of its parameters. But the other way is possible. If I have an animal box, I can assign it to a human box. So if I have a human here and assign it to a human is an animal, so I can assign it to the first input, the first parameter of put. It's fine. This is all safe code. So here you can put a modifier in front of the type parameter t. This means that this interface box only uses the type t as input to its methods. Here put is an input to the method. So that's why it's called in. It consumes it. But it means that the assignability is kind of the opposite way. So if human is a subclass of animal, the box of animals, so the box of animals is a subclass of box of humans. So it kind of reverses it that way. And then if it does both, like here, the list box is both a list and a box. So I produce it in the get and I consume it in a put. Then I cannot assign a list box of humans to a list box of animals or vice versa. Just that's not possible, because whatever I try to do, I either hit upon this situation, an error, or I hit upon this situation, which also can be an error. So that means there is an invariance. There is no way of putting that right. So you leave out the in and the out. There's no modifier you can make on this. So that is, if a human is a type of is a subtype of animal, a list box of an animal and list box of a human are not related. They are not subtypes of each other. Are there any questions about variance of generics? This is a little bit of a meaty topic, but it's pretty cool if you get the hang of it. And it's actually simpler than the one in Java, believe it or not.
Simple until you start getting into reified generics.
Yeah, yes. I didn't put that one in. There are some other things as well that are specific with type adjacent, so to say. But I just kept it to the type definitions itself. Yeah, that's another one. It's pretty cool what you can do with that. Okay, then this is the last slide of the Kotlin types. So this is recorded, and also we'll make these slides available probably on the GDG website. You will be linking those out, I presume.
Yeah, we will.
Okay, thank you. Yes,
Maybe in
absolutely.
the meetup, we'll post to the meetup.
Okay, perfect. Thank you very much. So yeah, so this was the last slide. So try to mull it over. There's a lot of information in this talk, but I basically hit upon all the variations of the typing that you can do in Kotlin, and allow you to basically research more in some type adjacent stuff, such as sealed data classes and reified types and all these other things, to get even more powerful typing out of Kotlin. Thank you for listening, and hope to see you around and maybe in Kotlin's office hours at another time.
Thank you, Anton. Alex, whenever you're ready, you can start. I don't, or unless you feel like we should take a little bit of a break. I think I'm happy to keep going.
Yeah, I'm fine to just dive right in if other people are.
All right. Sweet.
All right, let me try and share a thing. All right, can y'all see a screen?
I can. Yep.
All right, nice. On the last slide too. And we're done. All right, there we go. Okay, awesome. Well, howdy everybody. My name is Alex. I'm a mobile developer at a company called Geneva, which is making a new way to chat with groups. So the talk I'm going to give today is sort of just a high level comparison of RxJava and Flow. For anyone who's not super familiar with RxJava, I go through some pretty simple examples, so hopefully that'll get you up to speed. If something doesn't make sense, feel free to jump in and just ask any questions. Quick roadmap. I'm going to do a really quick introduction to reactive programming, very quick. I'm going to jump in a little bit in RxJava and coroutines, and then the meat of the talk is just walking through some comparisons with RxJava and Flow, and then some takeaways. All right, so what is reactive programming? I think that there are a lot of people, especially on the Android side, that kind of use some of these reactive constructs like RxJava without really employing any sort of reactive programming. So when I say reactive programming, what I typically mean is programming with some type of asynchronous data stream or asynchronous data format. And then really importantly, like propagating change and then reacting to that change. Some of the benefits are it keeps your data up to date and it allows for very, very declarative code. So if you really want to like get a good look at a very reactive code base, the Kickstarter Android app is a really interesting example. And you can see kind of what code that just goes all in on reactive programming ends up looking like. It gives a lot of like very declarative blocks of streams and then very declarative inputs and outputs. And I think it's pretty beautiful. So how do you do that? How do you typically achieve reactive programming and employ some of those reactive paradigms? Streams. Look at how beautiful this picture is. Look at this wonderful place that none of us can go to now. Streams. Asynchronous streams really make a big difference there too. So what's an asynchronous stream? So this is an RxJava marble diagram. A marble diagram basically shows the timeline of an observable, which we'll talk about in a minute. And you can kind of think about it as like a list where time is another dimension. So like an asynchronous list. So as our arrow moves to the right, different events come through, and then eventually you'll see an error or your stream will complete. So here's an example building up a little observable. An observable in RxJava is just a thing that emits values over time. Again, like a list is a really good comparison, except there's maybe 5 seconds between each item in the list. In this scenario, we're creating an observable that'll tick every second and pump out a new value. So every second we'll get some integer, I think it's counting up. And then we kick off the whole thing by subscribing to it. So when you subscribe to the observable, that starts the whole chain. And it's how you receive sort of like callbacks and you can actually do something with that data. Oh, I highlighted stuff. Here's a nice little GIF kind of demonstrating what the above would look like. So you can see every second a new value is emitted, and that just keeps going on forever. So the interval observable creator will just go on forever until you stop it. One of the cool things about RxJava and kind of using these asynchronous data streams is that you can manipulate them a lot. So you can take each item and map it, filter it, group it, do all of this different stuff as it comes through in real time. So we talked about how this this call interval will create an observable that keeps ticking infinitely every second. But we might not want that. Maybe we only want to tick like 3 or 4 times. We can use the take operator, which is just a function you apply to an observable that gives you another observable, to only take the first 4 values and then stop. And if we run this code, then we end up with something like this. 1, 2, 3, and we get to the last item and we stop. So rather than going on forever, it takes 4 values and then it ends. So that's a really quick intro into some reactive concepts and RxJava. Not a deep dive into RxJava, but maybe enough to get you a little bit of context if you're unfamiliar with it. So the really interesting part of this talk is comparing Flow with RxJava. So quick introduction to Flow for those of you who aren't super familiar with it. Flow is cold streams implemented with coroutines. And when I say cold streams, what I mean is a stream that won't start executing until you subscribe to it. Like, it won't start kicking and doing its stuff until you say, hey, I'm ready to start receiving things. It respects structured concurrency and all the stuff that we've come to know and love with coroutines. It's very heavily inspired by existing reactive framework that as we go through some of the examples. It's got a fairly simple design and API. So without further ado, let's just kind of jump right into some of the comparisons between RxJava and Flow. So if you want to create an observable, there are lots and lots of different methods. One of them, probably the most simple, is the just operator, or the just like factory function. So you give just something, and it'll create an observable that emits that something and then finishes. Very, very simple. So in this case, we're creating an observable that emits just the integer 1 and then finishes. On the Flow side of things, there's a top-level flow of function that does basically the exact same thing. You give it some value. We'll see later on how you kind of subscribe to it and kick it off, but you'll get that 1 value and then you'll finish. You can see it's already a little bit more Kotlin-y. It's a top-level function rather than like a static method on something. So that's one of the benefits you get with Flow. So it's very Kotlin first. Another common thing that you might end up wanting to do with asynchronous data streams is constructing them from some type of iterable. Maybe you have a list of things that you want to convert into a stream. With RxJava, there's a from iterable factory function that'll give you back an observable. And with Flow, again, we see it's pretty Kotlin-y. There's instead an extension function on iterable that'll give you back the flow. So this will have a flow that emits 1 through 10 and then finishes. A lot of times you want to kind of bridge the reactive and non-reactive worlds. Like maybe you have a callback or you're getting, GPS updates through the Android location manager, and you want to convert it into a stream. With RxJava, you'd use the create operator. That gives you this emitter object, and you can just pipe values through the emitter object as you see fit. So again, you see it really often when you're kind of bridging those two worlds. Again, Flow has an answer for that. It's the Flow DSL. So again, super Kotlin first, top level Flow function. It's an extension function with a receiver, and then you can just emit off the current object and emit whatever you want. Very, very similar. A little bit less verbose with Flow. Observing streams. So here's where things start to get a little bit interesting. In RxJava, you typically use the subscribe function to sort of kick off an observable and start getting stuff back and start listening to values as they come through the stream. You also get back a disposable, which is your way to say, hey, I'm done listening to this. Clean it all up. Nobody cares about it anymore. With Flow, you have the collect function, which is similar to subscribe in that that's what kind of kicks off the whole thing. You notice you don't get, well, you get back a job, but you don't really need to care about it because since you're in coroutines world, you're going to be in some scope and the scope's going to handle clearing everything out for you, which actually brings us to an interesting tidbit with this. If we were to toss in this flow.collect call in some random bit of code, we'd actually get an error. And to figure out what the error is, we can kind of dive into the type to see what's going on. So this is the type signature for collect. I love it because there's so many keywords. You know, it's great when there's 4 keywords before you even start your function. But the only thing that we really care about right now is the fact that collect is a suspending call. So when you're going to actually start receiving the values for your stream, you need to be in some suspending context. So to go back to our previous code, we kind of fix this up by using some coroutine scope that we have floating around and calling launch on it to actually collect the flow. So this, in my opinion, is one of the most interesting things about Flow. And the fact that collect is a suspending call actually enables some really interesting design choices that the team was able to make. So applying operators. We talked about this a little bit earlier, but in RxJava, or one of the nice things about these asynchronous data flows is that you can kind of manipulate them, you can filter them, you can map them, group them, all that sort of good stuff. RxJava exposes those across all of its types. Flow predictably does all the same stuff. So you can filter, you can map, all that good jazz. They're defined as extension functions on Flow, for whatever that's worth, if that means anything to you. Another thing that we all know and love in RxJava is changing threads. So I'm sure everyone's written this code if you've done any RxJava, but you use the subscribe on and observe on operators to change what threads your code is running in. On the Flow side, there's a similar flow on operator to figure out what's happening above that. Another thing we'll get into a little bit later, but one of the interesting things about Flow is since it's so hooked into the suspending world and or into the coroutine world, and coroutines have like a much cleaner answer for sort of doing this threading work, I find myself writing like needing to use flow on, needing to manipulate my threads within the flow much, much less. So that's a nice benefit that we'll talk about a little bit later. Pretty similar, right? So let's get into the interesting stuff, the actual differences. My favorite example of one of the big differences between Flow and RxJava comes up when you're folding a stream. So for those who aren't familiar, the fold or reduce or inject operator, it's called different things in different languages and stuff, is basically a way of walking down a list or an iterable or an observable and taking all of the values and accumulating them up into something. So here's an example. We have some observable. It is made up from the list of integers from 1 to 10, and we call it reduce, which is what RxJava calls it, with an initial value of 0 and an accumulating function that basically takes that initial value, adds the value we're getting back from the observable, and then passes it through to the next iteration. So what this will do is we'll start with 0, we'll add 1 to 0, then we'll add 2 to the result of the previous thing, which is 2 to 1, then we'll add 3 to the result of the previous thing, which is 3, and so on and so forth. So it adds up the integers from 1 to 10. In Flow, we have the same thing. They call it fold, but basically doing the exact same thing. But just like we saw when we called collect, this actually won't compile, we'll get an error. As always, let's take a look at the types to figure out what's going on. So if we look at the RxJava types, this is the type signature for the reduce function. The stuff that we actually care about here is that it returns a single. And that makes a lot of sense because when you're kind of combining up all of these values in the observable, when you're reducing over the whole thing, you only get back one final thing, like the final result of applying your function on that accumulator over and over again. And RxJava represents that as a single. RxJava also has maybes and completables and other ways to sort of represent these asynchronous constructs across, that may contain different numbers of values. So that begs the question of what is a single in Flow? Like what is Flow's answer to this? So let's look into the Flow fold type. Let's see what we got. Again, we have even more keywords, which is super fun. But the stuff that we care about are these two. So just like collect, fold is a suspending call. And if you look at the return value is actually the type of your accumulator. So that means that fold, unlike map or filter, is actually a terminal suspending operator. And the thing that you get back is just that raw value. So if we're walking through our flow that's emitting integers from 1 to 10, what we're going to get back, the result of the call to fold, is just going to be an integer. It's going to be the final sum of folding through those numbers. So what's a single in Flow? A single in Flow is just a value. There's no extra overhead needed. You don't need another wrapping type. to represent a single value in flow. Because you have that suspend keyword there, you already know that you're in like a deferred context, and you can just operate on the fundamental types. And that ends up being really nice because it means that we don't need single, we don't need maybe, and we don't need completable. That's just a value, a function that returns unit, and a nullable value. It's just the normal things within the type system. And that ends up eating away at a lot of boilerplate. So I mentioned that fold is a terminal operator. There's a bunch of other terminal operators. There's also a reduce function. If you're getting like the first value out of a flow, that'll just return that value. It'll be a suspending call and you'll get back the value, which again is really nice because when you're in RxJava, you end up having this single and then you need to go through the song and dance to kind of get your value out of that thing when all you really care about is the fundamental value. If you're wrapping up a flow into a list, that's going to be a terminal operator. You're just going to get back your list, so on and so forth. So that's something that I find really cool about flow and something that I think enables flow to reduce the amount of boilerplate that you need to deal with a lot. All right, so observing multiple streams. This falls into the gotcha camp. So let's say you have multiple streams, or let's look at an example of multiple streams in RxJava. We have some observable that's going to emit a bunch of names, Alex, John, Daryl, and end. And then critically, it's going to delay by 3 seconds. So what the delay operator is going to do is it's going to cause this observable to only start emitting its items after 3 seconds. So we'll wait 3 seconds, then it'll emit Alex, John, Daryl, and end. And then we have an observable of integers, and that's just 1, 2, 3, and 4. Pretty simple. We subscribe to our observable of names, and we just print each one out. And we do the same for our observable of integers. Now, what would we expect to get from this? What I would expect to get from this is I would expect 1, 2, 3, 4 to print, and then after about 3 seconds, Alex, John, Daryl, end to print. Because since names is being delayed by 3 seconds, and integers is starting to print immediately afterwards, it should just immediately get into integers printing and then go to names. And that's exactly what we get. We get 1, 2, 3, 4, Alex, John, Daryl, end. So I was right. Amazing. First time. Let's look at multiple streams with flow. So same thing. We have a list of names. Apparently I forgot the end name. Nice. Flow doesn't have a delay operator. Instead, it gives you a hook in when the flow is about to start emitting, and you can do whatever you want. And since it's a suspending lambda that you get to pass into on start, you just use the delay function that you would in normal coroutines. Another really nice thing. And we have our list of integers, just 1, 2, 3, 4, which we're converting to a flow. Then we call names.collect, print them all out. And we call integers.collect and print them all out. So again, what would we expect to get from this? If you've used coroutines and flow a lot, you probably know the answer. But for me, especially when I was first starting, I would have expected to get the same thing I got back in the RxJava case. I would expect to see 1, 2, 3, 4, 3 seconds to go, and then Alex, John, Daryl to print. But that's actually not what we get. Instead, what we get is the strings printing and then our integers. And to be more specific, what we get is a 3-second pause and then our strings printing and then the integers. Now, what's going on there? So we mentioned before that collect calls suspend. It's a suspending method. And what that means is that the next line after the first names.collect is actually only going to fire after the names flow finishes. So you won't see anything after a call to collect until that flow finishes. For a lot of us in the Android world, at least, that is that can create some nice traps. So let's say that you're listening to a flow of orientation changes. Maybe you're modeling that as a stream. Well, that's never going to stop. That's going to be going as long as your application is alive. So if you have code like this, where you expect some code to run after that, it'll never run and you'll be sorely disappointed. Okay, nice highlighting. So there's a couple ways around this. The first one that you'll see in docs is you can just call launch within whatever scope you're in, and do that multiple times for each call to collect. And now they won't block each other's launches, and you'll get what you'd expect. So if we run this code, we'll get 1, 2, 3, 4, Alex, John, Daryl, which makes sense. For those of you who are more, for those of you like myself who are more inclined towards the sort of builder pattern that RxJava uses, there's another way to do it where you use the onEach operator, which just lets you do some action as each item comes through. And then the launch-in operator, which is a terminal operator that'll start off your whole flow where you can pass in some scope. These are semantically the same thing. I just like the way on the right. It's more familiar to me personally as an RxJava user. So the next thing I want to talk about is the role of FlatMap. So how have we been using FlatMap? I think that there's two really good usages for FlatMap. The first one is to transition between all these different Rx types. So if you have an observable and you want to get a single, you want to like take some action on a single for each item in your observable, you're going to use FlatMap single. If you have a single and you want to convert yourself into a completable, you're probably going to use FlatMap completable. And so there's, 12 or however many methods between observable, single, completable, and maybe to transition between all of the different types. Also, the other usage is to actually flatten multiple observable streams into one. So chances are, if you're like me, then you've used FlatMap on regular lists a few times. So if you have like a list of lists and you want to flatten it into one, then you'd use FlatMap for that. Similarly with observables or streams, if you have an observable of observables, you might want to flatten that out into one observable. I can't speak for anyone else, but transitioning between different types or from one observable that emits one thing to another observable that emits one thing is how it was about 99.10% of my FlatMap usage. I think I could probably count the number of times I've actually used FlatMap to like flatten a stream on no hands because I've never actually done it. So here's a good example of how I think a lot of us in the RxJava world end up using FlatMap. So let's say we have some API where we're fetching a list of cats, cat names, let's say. And then we have some stream that represents refreshes. So maybe like a pull to refresh sort of a thing. So every time the user does a pull to refresh, this refresh stream will fire. Then maybe we want to fetch our list of cats every time the user does the pull to refresh. Well, then we'll use FlatMap single because fetch cats returns a single, and we can't map between observable and single. So we have this extra step to do FlatMap single there. And we subscribe to it and we get to display our cats. Nice. So any Android developer, at least, who's used RxJava has almost certainly written code just like this. So now let's look at that example in Flow. So what would our API look like? We don't have a single. That doesn't make sense in the Flow world. Instead, we just have a suspending function. And the type of that is just a list of strings. It's just the cat names. We don't need that extra wrapper of a single around it. And then we have our refresh stream. Just like before, that's a flow that emits nothing whenever the user does the pull refresh. We've got our refresh stream. And now, instead of using FlatMap or FlatMap single or anything like that, we can just use the map operator. The lambda that you supply to a lot of these flow methods like map and filter and so on are suspending lambdas, which means that you can just make calls like fetch cats or any suspending call within the map. You don't need that extra layer of FlatMappy boilerplate to do this sort of stuff. And it may seem subtle, but in my mind, or from my experience, it's a meaningful cognitive burden to go through all of the different FlatMap types and to try to figure out what type you're interacting with at that point. And Flow really simplifies that by just having your normal Kotlin types. And then you call collect and you display your cats. So the next thing I want to talk about is error handling. So in my opinion, error handling is the hardest thing about RxJava. And there's lots and lots of hard things about RxJava. But error handling is where everything breaks down into a point where you realize, oh, a lot of this stuff isn't going to work. And a lot of this logic is going to get really complicated really quickly. Anyone who's tried to write like an exponential backoff in RxJava has Googled, found on Stack Overflow, that same code that uses retry when and emits different observables and binds to those observables, knows what I'm talking about. So let's take a look at some error handling in RxJava. Let's say we have a puppies stream. Now this is just going to be an observable that prints out puppy names. We're using the create function that we saw earlier. We emit Fido, Fluffers, Peanut, but then oops, something happens and we have to throw a runtime exception around a puppy crash that's happening. A puppy crash, the best type of crash. If we just subscribe to that puppies stream, then whoops, something's going to go down here. We're throwing that runtime exception and we're going to get a crash. Instead, what we have to do, and again, anyone who's written any RxJava has made the mistake of writing this code and then has seen a very opaque stack trace in Crashlytics or whatever. You have to add sort of an extra block of error handling. So you add that new lambda in there, that'll handle the error. Now you won't crash. Instead, the error will go through to that second lambda and you'll throw it away and ignore all the problems in your code base. Wonderful. So let's take a look at errors in Flow. Just like before, we're using that Flow DSL. And just like before, we have a puppy crash. And we're calling collect, but we're not handling the error, so we're still going to crash. So what do we do about it? So one option is there are similar operators to kind of catch errors, like within the stream, the way you would see in RxJava. But another thing you can do is the thing that everybody tries to do when they first start learning RxJava, which is you can just wrap the whole thing in a try catch. And this to me is where you really start to see some of the dividends of collect being a suspending call and having that like having completion after your call finishes. Because this collect call will just throw the exception, so you can just try catch it normally. And you definitely can't do this in RxJava, and it's very frustrating when you first learn. So this sort of thing, error handling in Flow, is something that I'm really excited about. So custom operators. There's a few custom operators that I tend to bring with me to every different project I go to when I'm writing, when the project uses RxJava. One of the main ones is sort of like a sliding window. And when I say sliding window, I mean something that kind of buffers, but will immediately emit some items before it gets to its buffer. So here's a little image of it, and please marvel at my Photoshop skills. So let's say the stream we have on the left is just a stream that emits values from 1 through 6. And then we want to apply our sliding window operator, and what we want to get back is a stream that first emits a list with null and 1 in it, and then after that emits 1 and 2, and then 2 and 3, 3 and 4, so on and so forth. Basically, we want to get windows of 2, but critically, we want to get that first window immediately. So I want to operate on this first thing as soon as I can. That's something that I find myself needing to do all the time. For some reason, there's no operator for that in RxJava, so I end up writing it a lot. So let's write that operator in RxJava. And to be fun, let's write it in a super unsafe and racy way that should never make it into any production code base. So here's a really simple implementation of sliding window. Writing custom operators has admittedly become a lot easier in RxJava since we got Kotlin, because you can just write them as extension functions rather than going through the whole horrible compose transform concept that we used to have. So here's a little breakdown of this code. So we're writing this sliding window function. It's going to take some size. That's like the size of that window. And we're going to get back an observable of lists of items. So if we have an observable of integers and we call a sliding window with the size 2, we expect to get back an observable of list of integers where each list is of size 2. So what we can do is we can just kind of make up a mutable list and then kind of hook in with the doOnNext operator. And so every item that comes through, we can check the size of our list. And if the size of our list is as big as the window size that we're passing through, then we just remove the oldest item and add in this new item. And then we omit that list. We make sure to make a new copy of the list because we're good citizens and we don't want to mutate our list. So there's some race conditions with this code, but whatever, it kind of gets it done. So let's look at that same operator in Flow. So first off, we can look at the header. Just like before, we have some generic type, and we have some window size. Just like before, this will return a flow of lists of t. I forgot the type there. Whoops. Now let's kind of take a dive in here. So we saw this earlier, but we're going to use the flow DSL. So this is already interesting. In our RxJava code, we kind of found an operator that let us do what we wanted to do. And that typically is how most custom Rx operators end up working. You end up in a world where you're saying, oh, it turns out I can use map here and group by here to get the thing that I want. And if you don't have those operators to really get the thing that you want, then you enter a much scarier world where you have to write a lot of very challenging code. But in the flow world, we're just creating a new flow. And that's an interesting paradigm shift. So just like before, we build up a mutable list. And then, unlike before, what we do is we just start listening to our original flow. So this is an extension function on a flow. So we can just call collect and then do our logic in the body of that collect call. And that to me is kind of revelatory. Since we have the flow DSL up there, we have the ability to emit items into that flow DSL, and then we can just do normal logic. We don't need to kind of rely on all of these different operators to try and hobble together the thing that we want. We can just start listening to items and manipulate them however we want. There's also a transform operator that you can use, which is kind of parallel to creating custom operators because it lets you emit whatever items you want in the middle of the stream too. So I find this another very cool thing about Flow. And one of the stated intention of the authors behind, the authors behind Flow stated that one of their intentions was to make writing these operators trivial. And it mostly is, as long as your operator is not too crazy. So that's really nice. I'm a huge fan of it. So downsides, I've talked a lot about kind of the pros of, the ups of flow. So let's talk about a little bit of the downs. First off, there's no share operator. There's no like publish or ref count operators either. For those who haven't used the share operator is a way to kind of take a cold stream and share it between multiple subscribers. For me, it was actually the operator that kind of unlocked this sense of like, oh, I can make a network call and then kind of split it up into lots of different observables and act on them all independently. And it really sort of felt like it enabled me to do reactive programming in a big way. And it's just not possible with Flow right now, or at least not realistically within your project. There's an open GitHub issue, and my understanding is that they're working on it, but it's not quite there yet. And it's not an operator that you're going to want to write yourself. There's no chunk or traditional buffer operators, which is another interesting thing, and another thing that I believe they're working on. There's no replay operator. That gets into some of the share ref count stuff. A lot of the API is still very experimental. If that's something that concerns you, if you're very against using experimental APIs, then enough of the Flow API is experimental that you probably don't want to use it yet. This one might be a little more controversial, and it's not Flow specific. But in my experience, debugging coroutines is no fun. I've found that, especially maybe it's just Android Studio, but a lot of the debugging into coroutines ends up not firing or firing in wonky ways. So that is a pain point that has, in my current project, as we've transitioned from RxJava to Flow, that's been a very unwelcome surprise. So for some of those reasons, I'd say it's not quite ready to replace RxJava yet. You're definitely in a scenario where you can use it in production. And if you're not doing, like if the whole philosophy of your code base isn't reactive programming, then you could absolutely get away with using Flow for sure. If what you mainly get out of RxJava is, what you mainly get is just doing asynchronous work, then it's no brainer to just use coroutines. But if you're primarily using RxJava to just occasionally have some observables that emit stuff, then Flow is 100% there for you. And honestly, it's, for most new projects, I probably would recommend starting with Flow instead of RxJava. But if you're deep into the reactive weeds, then the fact that there's no share operator and no ref count and publish means that you might want to pump the brakes a little bit. And that's all that I had. Yeah. Thank you all.
Awesome. Thank you. Alex, quick question. What about the size of this library? I mean, RxJava is pretty big. Could you have both? Is that a problem?
You can definitely have both. Flow is definitely a smaller library than RxJava, but yeah, you can absolutely have both. In the current project I have, we have both because we're kind of migrating from RxJava to Flow. You probably wouldn't, like in a new project, you probably would not introduce both Flow and RxJava. They're competing for the same space. But when you're migrating, then you absolutely can have them side by side. And there's even a bunch of, there's a library that the Flow team has put out to move back and forth between the reactive spec RxJava types and Flow types. So they even give you nice tools to kind of assist in migrating over to Flow.
So assist with the refactor or bridge with
the bridge. Yeah, so if you have a Flow and you have some class that's consuming mostly RxJava types and hasn't really gotten into the coroutines world yet, then you can take a Flow, call a method on it, and get back a flowable, just an observable. You can get back an observable.
I have a, I guess, tangential question. One of the issues I find with coroutines is when you're trying to debug them with breakpoints. If you hit a breakpoint in a coroutine, it doesn't give you any information on the class or the object it's, I guess, hosted inside of. Any idea what the like if there are any solutions coming forward for that, or do you have a special way for handling that besides maybe logging or some other way?
So is that because you're inside like a view model scope? So this is the scope?
It's a perfect example. Yeah. View model scope, like launch from a view model scope, and then you have a breakpoint in that, inside that scope. And if you get there, you don't see any properties in the debugger of the view model you're in. You only see what's inside that scope.
So in that scenario, what I typically do is you can open up a little expression window within Android Studio, and then because you have access to that outer containing object. Like if you were in Kotlin code, you'd write this at my view model dot whatever. And so if you open up the expression window where you can start typing arbitrary code in your debugger, you can do that and then see all the stuff in the containing class. I think that's like a Lambda with receiver problem specifically. That's what I typically do in that case.
That's not
sometimes also what I noticed that Kotlin is very, very aggressive with stripping out outer scope that's not necessary.
Yeah.
So if you have an activity that you provided a Lambda, but you do not refer to anything of that activity in your Lambda, it will be a static object. So the activity is kind of stripped out. So if you're in the middle of it, you don't have access to your activity stuff because it's global. Sometimes just putting the word this at activity in there or something like that makes it work, at least for debugging purposes, and they can strip it out later, which is good. You leak a lot less, but it's but for debugging often it's like, why is this variable not available? I'm in my activity. What's going on?
Yeah. There's definitely some progress to be made on both the Kotlin debugging front and the Kotlin coroutines debugging front, and I'm sure that progress will be made. Any other questions? Anyone have anything? Cool. Well, thank you all for listening. Say it again.
Will you share the slides with us?
Yeah, of course. Yeah.
Awesome.